this talk is divided really in two parts. The first part is to discuss a bit what is this concept of the specific relative entropy between continuous martingales, a bit of its history, what has been done with it, a couple of the properties of the object. Then we cover an application, which is strictly speaking not in finance, but it's very related, you will see. And this is to so-called most exciting games. So let's discuss about entropy and continuous martingales, okay? So throughout the talk, M is going to be a continuous martingale, usually real valued, unless I say otherwise, and B is a Brownian motion. Relative entropy, this is a reminder, in case you haven't seen this, relative entropy between probability measures mu and nu is the formula that you have written there in case that the density of mu respect to nu exists, otherwise plus infinity. Now, maybe the key observation for this area and this talk is the following little computation. Obviously, when I have relative entropy, I will write either probability measures here or the loss of random variables, loss of random vectors, yes. So using that notation, I want to compute the relative entropy between the law of this random vector. It is a random vector which in each coordinate is sigma, a constant real number, times Brownian motion at a time of the form k over n. So that's in the first random vector, and the other random vector is the same thing, but I am not multiplying the coordinates by the constant sigma. So it's essentially the law of Brownian motion projected to the times of the form k over n, where n is fixed. And, you know, one of the beautiful properties of the relative entropy is that, you know, it is preserved under bijections. So you can pass, instead of the laws of these random vectors, you can pass to the laws of the increments of those random vectors, and the relative entropy does not change. If you pass to the increments, then, for instance, the increments of Brownian motion here are, you know, IID, but also the increments of this sigma times Brownian motion are IID. And for that reason, another so-called tensorization property of the relative entropy tells you that this entropy of the multivariate vectors becomes just n times the relative entropy of what happens in for each of one of those increments. So here I just took the first increment of the first guy, the first increment of the second guy. So this is the tensorization property. And now you need to, you know, do a couple of computations. It's completely explicit here when you have Gaussian densities and you apply the definition and you get this answer. Okay, so this you will have to trust me. And yeah, what we learn from this is that if we refine the time grid, so if we send capital N to infinity, we observe that in case the expression in parentheses is non-zero, then this relative entropy goes to infinity at the rate n. And it turns out the expression in parentheses is exactly 0 if sigma square is 1. So that means if here your sigma is not plus minus 1, then these relative entropies, as you refine and refine your time partition, is going to infinity. Now, this is one argument why the law of sigma times Brownian motion in continuous time has infinite entropy with respect to the law of Brownian motion in continuous time. But actually, this phenomenon is more general. So typical continuous martingales will have infinite relative entropy to each other. But the advantage of this little computation is that it suggests a possibility how to define a more meaningful notion of relative entropy between continuous martingales. Namely, well, why don't we just take, let's say, two martingales, M and M bar, with discretized time. We compare the relative entropies of these random vectors in n time steps, And now we normalize by n, and we hope to go to the limit. In the computation, that would have given us the expression in parentheses. So maybe this is a reasonable thing to do also for other more general continuous martingales. So this is the intuition why scaling makes sense for martingales in continuous time when we compute relative entropies. So indeed, this has been already defined, in fact, more than 30 years ago. So the object has been called specific relative entropy. And yeah, it's precisely the scaled limit of the relative entropies, as I just tried to motivate. There is no reason why the limit exists. So, okay, we take limit inferior, that's fine. So yes, this definition goes back to Nina Ganter's PhD thesis, I think 1991, which is in German. Here you have the title. And Nina Ganter was doing her PhD with Hans Vollmer, by the way, and as a supervisor. And in fact, in more recent times, Hans Vollmer himself has published a couple of works I cite here, which have repopularized this subject, and he has also extended Nina's original work. Now, to be more precise, this idea of scaling entropies and going to the limit is a more general idea. For instance, I've seen that people apply it when they study stationary process or random fields. So maybe the concept is much older than 1991, but in the context of continuous martingales, there is no question that this goes to Ganter's PhD thesis. Okay, now I take a little break because I know that people in math finance and control are quite used to working with relative entropies, and now I'm trying to tell you, okay, let's look at this other sense, this other definition. So I want to make a little break here to explain some connections to the literature in finance specifically. First of all, there is this paper by Avellaneda, Friedman, Holmes, and Samperi, I think 1996. I think they were not aware of the work of Nina Ganter. And in this paper, they have similar idea of saying, well, we want to compare two different models for stock prices in continuous time in the sense of relative entropy. We cannot. So why don't we approximate these continuous processes by trinomial trees? We compute relative entropies for the trinomial trees, approximating trinomial trees, and then we pass to a scaling limit. So that's precisely what these authors do. And then they come up with formulas for the limiting object, and these are loss functions that they will use for the problem of volatility calibration given option data. So that's all in that paper. So very related to what I just introduced. In more recent time, there is this article by Cohen and Dolinsky. They consider utility indifference prices in discrete time for exponential investors that are trying to price an option. And they pass to the limit as the number of time steps goes to infinity. And essentially, due to the duality between exponential utilities and relative entropy, this passing to the limit that they get there in the dual corresponds to something like the specific relative entropy. Okay, this is done under certain technical conditions that then were shown to be not necessary in the follow-up paper of Dolinsky and Zhang. So they really pass on to the limit without technical conditions, essentially, in these problems of discrete time exponential hedging. Now, so I would say these are the papers that are closest to the subject of specific relative entropy. I want to mention a couple more that are maybe less close, but I think still interesting to look at. So for instance, these two papers by Carmona and Xu and Henri Labordère more recently, they also consider the problem of model calibration when you have volatility uncertainty. And they also consider relative entropy as some sort of loss function. But what they do is that they consider actually stochastic volatility, where the vol of vol is known, but what you don't know is the drift of the stochastic volatility. So it's drift uncertainty for the stochastic volatility. And there they solve entropy minimization problems given option data, which is well posed because we're talking about drift uncertainty, even though what they're trying to do is to pin down the volatility. So this is sort of a related thing, but not quite to what we do. And I finally want to mention this work of Nutz and Wiesel. So they will also be solving, as I will do later, a problem of entropy minimization, but only in discrete time, given marginal information, given information of option prices at initial and terminal times, but in discrete time. Passing to the limit, if it would be possible in that paper, would be related to the specific relative entropy. Okay. So this is just, not an extensive list. I think many people have worked in finance in connection to relative entropy. Of course, we think of minimal entropy risk, Martingale measures, and so on. But these are the papers that are closest to what I'm talking about today. Okay. So recall specific relative entropy is the scale limit of relative entropies. Now, what caught my attention, why I'm working in this field right now, is this beautiful inequality that's in Ganter's thesis. It says that the specific relative entropy, so the scale limit of relative entropies, has a very neat lower bound. It is written here, and sigma square will be the volatility of the Martingale M. And you see, this is nothing but the expression that we already knew if the Martingale was just a multiple of Brownian motion. In that case, sigma square is a constant. So what you need to do for the lower bound is just to imagine that you integrate in time and in omega. And this is indeed what she proved. This is interesting because this lower bound now is in terms of something that we can try to estimate or we can try to control in a given problem, namely sigma. Now, for the intuition, maybe it's more informative to look at this equivalent expression when I pass here. So what's inside of the expectation is nothing but the relative entropy again, but now of the uniform random variable 0, 1 with respect to the random variable whose CDF is the quadratic variation of M. So now you can see if the specific relative entropy is small, it means that on average, the clock of your Martingale, which is its quadratic variation, is uniform in time, just like the clock of Brownian motion. So that's a bit of an intuition what this lower bound is telling us. Okay. So now I present the first of my contributions. So it turns out that the inequality, these arguments of Ganter were not very difficult to extend to multiple dimensions. So now you can have multivariate Brownian motion, a multivariate Martingale, continuous Martingale with quadratic variation. Let's call capital sigma this quantity. And then it's essentially the same formula, just the sigma square becomes the trace of sigma. The log of sigma square becomes the log determinant of sigma, and the 1 is just the dimension of your ambient space. So this is something that you obtain without too much work, I would say. What was interesting in this extension was that we explore a bit the idea of the lower bound being very sharp. So that's what you want to understand in this business. And we were in fact able to show that this lower bound, if you see it as a function of the law of M, is the convex lower semi-continuous envelope of the upper bound. So it's a very well adjusted to the left-hand side. Okay. The conjecture, there was a conjecture for a while, actually, ever since the PhD thesis of Ganter, whether this inequality, maybe in dimension 1 to be precise, if the inequality is actually an equality. And this is something that we will address in a moment. For the time being, we just know that the right-hand side is the convex lower semi-continuous of envelope of the left-hand side. So let me show a positive result when we can establish that these bounds match and there is equality. Yeah. So in this positive result, the martingale is solving SDE with time-independent and very regular coefficient sigma. These are the conditions that we use. So very, very well-behaved time homogeneous Markov martingale. And in this setting, we can show that indeed the lower bound and the upper bounds match. This was done in work with Unterberger. And I forgot to say the previous result was done with Bellotto, both of them students here in Vienna. So I want to give you a bit of an intuition. What are the ideas that are behind this kind of results? Remember that we already know that if sigma would be a constant, we already know the equality holds. This was the first computation of the talk. And therefore, the intuition is simply that, you know, if your sigma is so nice as I am requiring here, then the transition distribution, the transition probability, sorry, of your nice martingale are almost Gaussian as well. So this is the intuition, and therefore, if you already settled the Gaussian case, maybe you also settled the case of this kind of martingales. Now, the truth is that you want to compute scaling limit of relative entropies. So that means you need to understand the logarithm of the density of M to B at this time steps. That's why you need to understand the quotient of the density of M to the density of Brownian motion. And this is what we can do with Clara. We did it by hand, and it's not so hard under these stringent assumptions. One nice byproduct of this method was that we don't actually need the reference martingale B here to be Brownian motion. It could be a martingale which is in the same class as M. Then it would have its own sigma, let's call it, say, sigma bar. And then in this expression on the right, you would just have the quotient of sigma over sigma bar. So now we can say that the specific relative entropy between two nice martingales have a pretty formula in terms of the sigmas of these. So one thing that is open, and I've been giving talks this year a couple of times on this subject, and I keep advertising this, is how to significantly relax these conditions on sigma. I think it's good to understand how far you can push the argument. And yeah, I don't know the answer. So I'm happy if anyone can look at this question. And the other thing is that, what we did by hand here, this careful asymptotics of the quotient of densities, actually you can also do in higher dimensions, but now you don't do it by hand, you do it by so-called heat kernels estimates. And this has been recently, in fact, done by this group of authors in this paper. So now we know that there is a multidimensional analog to this result, thanks to the work of these authors. But the conditions that they have on their multivariate sigma are analog to these conditions here. So the question of how far you can weaken the assumptions on sigma is open, of course, in any dimensions. Okay. Now, before jumping to application, I jump once, maybe for the last time, to these bounds that we have here. I chose to motivate the object of the specific relative entropy via scaling limits, as Nina Ganter did. This is for historical reasons. But for me, the lower bound is the most meaningful object, because it's the lower bound which is bounded and it's a convex and lower semi-continuous. So it's the object that is going to behave better in your applications. So I'm an advocate of the lower bound, and in the talk I will be sometimes referring to either lower and upper bounds as specific relative entropies. Okay. But in the application that we will do now, although I will be concentrating on the lower bound often, at some point we will come back to this result and I will be telling you more about the conjecture of when the inequality becomes equality. So if there are no questions, then I will just proceed to the application.
There's a question on the chat.
Yes.
Which is about the drift case. What about the drift case? Instead of, I'm assuming instead of Brownian motion, you have a nice joint martingale with some drift.
Yes, very good question. So what happens is, yeah, if you would have a drift, this would disappear in the limit. So the scaling here by 1 over n would kill the drift in the contribution of the drift in the limit.
Okay.
So
and I also have a question, because if you define this way your specific relative entropy, I have the impression that you are counting too much the impact of earlier mistakes somehow, right? Somehow, right? For k equal to capital N, you are looking the entropy between the final points. And then I mean, at 0, they are probably equal. So you have a linear interpolation, right? There are n terms. Each one of them are probably of size k over n. You expect that the sum is of order n. Why don't you, instead of looking to something like this that degenerates, why don't you look at the relative entropy of the increments?
Yeah, well, but
this looks to scale better in time.
Well, it's a mirage, I think, because the relative entropy remains unaffected if you pass to the increments. If you take a bijection and push forward both measures, then the relative entropy, just by the change of variables formula, will not have changed. So as in the computation for Brownian motion here, I started with the path, this discrete time path, but then I passed to the increments. And you can show that the value does not change.
Okay.
So that's what I can say. Maybe a different type of critique, which I've heard before, is why do you take a regular time grid, you know? Yeah, this maybe I can comment towards the end again, but somehow the message is if your definition is better adapted, like to the setting of non-uniform time grids, then you expect almost the same theory.
Okay, thank you.
Thank you. Okay, so I proceed to the application. So the application refers to wind martingales, and wind martingales, here's the definition. So let's say in dimension 1 first, it's a continuous martingale, I will assume with absolutely continuous quadratic variation, which at time 0 starts at the deterministic position x0 in the interval 0 to 1. And at the terminal time 1 for us, this martingale is either 0 or 1. Yes. So this martingale, the distribution at time 0 is a Dirac at x0, and the distribution at time 1 is a Bernoulli with parameter x0. And in between, you know, it's moving continuously. So wind martingales have been proposed as models of prediction markets. Yeah. So prediction markets are markets that have been set up in order to assess the probability of an event in the future. For instance, I checked today, there is a prediction market for whether a certain candidate to become pope becomes a pope at the end of the conclave. there is a typical prediction markets in the past are prediction markets which try to say who will win, for instance, Harris or Trump. Yes. And yeah, what happens in the prediction market is, when you look at time t, the value that you observe in the market is supposed to be the probability that an event in the future is going to happen, given the information up to time t. Therefore, it's a martingale. And at the terminal time, everything has been revealed, and you know if the event happened or not. So its probability is either 1 or 0. That's why then win martingales are models of prediction markets. Yeah. Now, prediction markets were quite fashionable like 15, 20 years ago. Then I think the interest on them dropped. I think now they are again more fashionable, maybe because all the apps that you can use, all the websites and apps you can use to bet on these markets, or also because of COVID, that people had too much time. But now they're again sort of flourishing. Now, David Aldous has a very nice website with a glossary of open questions, and one of those questions was this one: what is the most exacting game, namely the most random prediction market? So this question actually decomposes in 2 parts. First of all, what is the amount of randomness? Or how do you measure randomness? Because we will be talking about continuous time martingales. So the first part of the question is, formalize mathematically what the question is, and the second part of the question is really to answer that. And as we have seen in this talk, the typical candidate of a quantity that measures randomness is differential entropy, or just entropy, let's call it, as we know from physics and so on, statistics. But in continuous time, this is a not well-defined object, the same way as relative entropy is not well-defined. So that is a bit the difficulty, how to define this, properly state the question and then answer it. Now, Aldous in his website also had some nice notes that suggest a possible road to answering the question. So in these notes, he suggests discretizing time and space. There we have a discrete time, discrete space martingale. We can define its entropy in the classical sense, try to maximize it, and then try to take a scale limit of that. So this is all heuristically explained in the notes. We follow more or less the same spirit. It's just that we will only discretize time, because as you will see in a moment, we will make use of specific relative entropy, which does not require discretizing space. So I think this is the key to the matter, if you ask me. So let's think of discrete time problems. Let's say a problem in n time steps. Yeah. P is n step martingale, and we know its initial law, it's mu, and its terminal law is nu. Okay. So mu will be Dirac at a point, and nu would be the Bernoulli. Now, gamma n here is just, let's say, Brownian motion discretized infinitely many times. So a Gaussian random walk. And let's see what happens with the relative entropy of P with respect to gamma n. So this is the expectation under P of the logarithm of the density of P to the density of gamma n. Now, I am abusing the notation, and I still call P and gamma n those densities. Assume that the density of P exists, of course. So I can separate the log of the relative density as this difference of logarithms. Now, the first term here is expectation of the log P dP is minus what people call the differential entropy. So essentially the relative entropy with respect to Lebesgue measure. And what about this other term? So gamma n is the density of the Gaussian random walk. That means gamma n is of the form E2 minus a sum of increment squares. we have logarithm of that, so what survives of that is just the sum of the increment squares, essentially. And now we're integrating under a Martingale law the sum of increment squares. So we know that this is going to be the difference between the second moments at the end and at the beginning of times. And because we know the distribution of P at the end and at the beginning, that is a constant that only depends on mu and nu, but not on P. Okay, so this is the important step. From now on, in this couple of slides, I will be discussing results jointly with Matthias Weigelbuch. And this was our first observation. If you would like to solve this sort of, this is actually a Martingale transfer problem in discrete time. So you're optimizing over Martingales in discrete time with given initial and terminal distributions. And you're trying to maximize the differential entropy by the above computations. This is equivalent to minimizing the relative entropy with respect to the Gaussian random walk. Okay, and now comes a bit of heuristic, I admit. So now this is we did in discrete time. Suppose that we would divide by 1 over n. The problem does not change. The minimizer does not change. So now we have 1 over n, this relative entropy. And now suppose that we could pass to the limit. We would obtain, therefore, the specific relative entropy as the cost criterion in the scaling limit. That's why, for us, the way to interpret Aldous' question was to minimize the specific relative entropy over Martingales, which start in the Dirac at x0 and finish in the Bernoulli center at x0. Okay. And by the arguments that I gave above, the cost function that we minimize is the actual regular version, the convex and lower semi-continuous version of the specific relative entropy. Okay. So in this article, we just do these heuristic steps, and then we go on to solve this problem without showing convergence of discrete to continuous or anything like that. So we are only interested in solving this continuous time problem here, which I am restating here. The same thing, but now I'm telling you, M is a Wien Martingale, so it means it starts at x0, finishes in Bernoulli. So this shows that this is some sort of a stochastic control problem. Yeah, you're controlling sigma, but there is a distributional constraint at time 1. So that makes it not completely standard. Okay. So this is the problem that we would like to solve. It's a very particular case of what's called Martingale optimal transport in continuous time. So now I want to tell you how did we go on to solve the problem with Matthias. So you need a good guess. And the guess here was as follows. So the relative entropy has a nice time decomposition property. So it the joint relative entropy decomposes as a relative entropy, let's say, of what happens up to time t, and plus a conditional relative entropy of what happens after time t. There is this beautiful decomposition of the relative entropy. If you play around with that, this suggests that solving the problem that we want to solve in the interval to 0, 1, well, if you would look at the interval from t to 1, that sub-problem looks exactly like the original problem. It's just that your time span went from 1 to 1 minus t. Because of this symmetry of the problem, you would expect that the optimal volatility also scales in that way. And that's the ansatz, the guess, the educated guess, that sigma tx decomposes as a function sigma x and something that scales with 1 minus t. And this is the right order, okay? So yeah, if you don't believe this, then the next thing you can do is consider separation of variables, and then you show that the time-dependent variable is this of this form. So we start with that guess. The other key of the argument, the key aspect of the argument is, well, this problem has very neat first-order condition because, yeah, if sigma will be optimal, then you can do time change of sigma, a very slight time change of sigma, that maps the interval 0, 1 to the 0, 1. And this would be giving you a new martingale, a time change martingale, which is suboptimal. And you do the asymptotics of that, and you get the first order condition, which is that the log of sigma is a martingale when sigma is the optimal coefficient. And now you just plug in Ito formula, the separation of variables, and this will give you an ODE for sigma x, and you solve this ODE, and you get to the explicit form of the optimal volatility. It's what's written here. Okay. Now, this is how we did it, but now I understood this from talking with Xinjiang, that, okay, you can also define a value function here and try to push the Hamilton-Jacobi-Bellman approach, and then you will also get here. Now, if you do that, there is a crucial thing that you need to note, is that you have a distributional constraint at time 1. In principle, it could destroy your your value function. Maybe does not depend on time and space, because there is a distributional constraint. It could destroy the argument. However, what you realize is that when you say split the problem from time t to time 1, and at time t you find yourself at the point x, then you know the distribution at time 1, because you have to be supported on 0 and 1 exactly. So you have to be a Bernoulli center at x. So the distributional constraint sort of updates itself automatically. You don't need to keep track of it, or you don't need to estimate it. Yeah. So if you do that, then you can also push the stochastic control approach and get also that this is the optimizer, and it's the unique optimizer, and we called it Aldous martingale because this is a problem motivated by Aldous. And yeah, as a sanity check, you can see that remember the martingale starts at between 0 and 1, so this number here is between 0 and pi, so it's not 0. And then it will never be 0, the numerator, until the time t equals to 1. At the time t equals to 1, because the denominator is diverging, this forces mt to go to either 0 or 1, so that the numerator would also go to 0. So it is a win martingale. This can be verified, and yeah, then you do verification and check that it's optimal. One thing that was nice is, okay, not only we provided a solution to all this question, but actually this helped us realize that we have answered the conjecture concerning the inequality between upper and lower bounds for the specific relative entropy, in the sense as I will describe now. So this Aldous martingale, the quantity that I have in the expectation will be finite for it. You can prove it. But on the other hand, when you look at the original definition of the specific relative entropy, there will be the point k equals to n, as Ibrahim asked. So there we have m at time 1. That is a Bernoulli. And here we have Brownian motion at time 1. That's a standard Gaussian. And this relative entropy is then infinite for every n. So what happens to the Aldous martingale is that the original definition of specific relative entropy is infinite, but the lower bound is finite. So yeah, the equality cannot hold always in that conjectured result. Okay. Now you can perturb this problem a little bit, and then you can even show that there are martingales for which the upper bound is finite, and it's different than the lower bound, by the way. So, okay, now I want to say at the same time and independently of us, this group of authors were looking at the same problem by Aldous, and they came to a different solution. The reason is that they stayed closer to Aldous' program of discretizing time and space, and so they obtain a different formulation in the limit as n goes to infinity. So essentially, they solve this same problem I'm sharing here, just that you don't integrate until the terminal time, but you just integrate until the first time that you hit 0 or 1. That's the only difference. And so their martingale is allowed to hit the boundaries before time 1. And in particular, it will not have separation of time and space. Yeah. So it's a harder problem to address what they did. Okay. There are lots of questions that remain open, even in dimension 1. For instance, you would believe that what we call Aldous martingales and the solution of these authors might be different, but maybe at an infinitesimal scale, they're not so different. One could try to think about that. A more concrete question which was also asked by Aldous, is now that you have found a martingale that's supposedly the most random martingale, the most random prediction market, can you tell me something about this distribution at given times? So for instance, at the time 1/2, what is the distribution of M? So this is something that we could not answer. And for the martingales that these authors studied, they could only approximate, I think, numerically the same question. Also, they don't have an explicit answer. So I want to give you now some intuition, a bit what these martingales are doing. So yeah, let's start not with the Aldous martingale, we'll start with a different wind martingale, also to convince you that there are plenty of wind martingales out there. This wind martingale is defined as follows. So at time 1, it's going to be 1 if Brownian motion is positive, and 0 if Brownian motion is negative. Yeah. So therefore, it's Bernoulli with parameter 1/2 at time 1. And to define it at the times before 1, you just take conditional expectation of this quantity, given the information of Brownian motion up to the time. So this defines a Brownian martingale. And here I'm displaying a few simulations of the paths of this, what we call Bass wind martingale. And you can see that indeed it finishes at 0 or at 1, at time 1. And when I do a lot of examples of the same martingale, you can see a picture like this forming. I would say that this martingale explores the available space pretty quickly. Now, when I look at the Aldous martingale, so this is what we call the most random martingale or the most exciting game. So here are a few paths. Well, you don't see that well, maybe that they finish indeed at 0 or 1 because of numerical error. So, but trust me, it is a wind martingale. And if you simulate many paths of the Aldous martingale, you get this picture. And maybe if you can compare it to the previous one, you can see that the Aldous martingale, this is the Aldous martingale, tends to spread out more evenly than the Bass wind martingale. So if this martingale is describing a game, remember that means that, for instance, at the time 0,2, I look at this, I see a value. That means that the value that I observe, let's say 0.65, is the probability that the event in the future will happen, given the information up to the time 0,2. So at the time 0,2, the outcome is quite open. You still are not very sure what's going to happen in the future. Whereas here at the time 0,2, for instance, you have paths like that, where the game is already almost decided. Like the probability of the outcome happening in the future is close to 1 or 0. So in that sense, you could say, yeah, this is describing a more exciting game, a game which is open or interesting for longer. This can be a bit justified better, as we did with Xinjiang. If you take any given time t, let's say here 0,4 or yes, 0,5, then the distribution of the martingale at time 0,5 of the Aldous martingale at the time 0,5 is smaller in convex order than the distribution of the Bass martingale at time 0,5. So that's a proper way of saying that this one is more widespread than the other. Okay, so that was just to give you a bit of an intuition. And now I come to the last I don't know how much time I still have.
You have 3 more minutes, I would say.
Okay, thanks.
Or you can take 5 minutes if you wanted.
Okay, thank you. I finished now describing a work with.
Before you go to that, there is a question on the chat.
Oh, great.
How do you test if the martingale truly covers the entire space? Quite often, graphs can be misleading. This is a question from Yanis Siligakis.
Okay. No, its density at every time is equivalent to Lebesgue. So at every fixed time t, you know that the density is equivalent to Lebesgue. And this happens for both martingales.
Okay. Thank you. And also, Valentin Tissot Daguet asks, what is the least exciting game?
Yeah, well, I would say first you need to explain mathematically that question, and then you can answer it. Yeah, it depends now how you define it. For instance, the game which is constant 0,5. So you at no point have any clue what is what the outcome is gonna be, and then exactly at time 1 it jumps to 1 or 0. Maybe that's the least exciting thing that there can be, but it's not clear. So maybe already at time 0, you jump instantly to 1 and 0, and then stay constant. So maybe that's the least interesting. So I don't know.
Okay.
Yeah. It hadn't occurred to me. Like, good question. Okay, so I come to the last slide. So here we're trying to go to multiple players, or let's say multiple outcomes. So think up to now we had an election with 2 candidates, Harris and Trump, let's say. Now we have multiple candidates. So for instance, now the conclave to become the Pope. Yeah. So we have the events or outcomes that could happen, or the candidates who could win. And MIT is the probability that, let's say, candidate I wins, given the information that we accumulate up to time t. So this is now what we would call a multivariate win martingale. Well, to be a multivariate win martingale, I should tell at time 1, only one player wins. That means that the vector with the coordinates at time 1 is either the canonical basis of RD, or is the vector of zeros in case none of the players win. So that's what we call a win martingale. So it's a martingale that lives in the subprobability simplex, and it finishes in the vertices of that. And we want to solve the same problem as before. In the multivariate version, I just discarded the 2 other terms that play no role in the problem. And very quickly, I just tell you, it turned out to be much harder to solve this problem. This was done work with Zizi Wang and Zhang. And Xin, by the way, is now at NYU in the group of Nizar Tuzi. And yes, so you see that for the Aldous martingale, we can explicitly tell you what is its volatility coefficient. And for the multivariate version of the Aldous martingale, we have like a similar expression, but it's in terms of this function g. Now, this function g is not known explicitly, unlike the one-dimensional case, but it's a unique smooth solution to some an elliptic PDE. Yeah. So yeah, in this work, we really follow the stochastic control approach with viscosity solutions and so on. What happens is that the value function decomposes nicely into time and space, and the space part of the value function is g, what appears here. And well, the stochastic control approach eventually tells you that the value function solves this, the spatial part of the value function solves this PDE, and if you can solve it, this is the optimal coefficient. Now, the hardest part in this result is to show that this is a win martingale. So to guess it, it's not hard, but to show it that it's a win martingale, it's hard, because you want to show that this martingale finishes at the vertices of the domain where it lives, not at a face, not at any face, but the vertices. And this was quite hard, and I have to say I wouldn't have managed. This was the magic of Wang and Zhang, CZ Wang and Xinjiang. They are they did awesome work to show that specifically, and yeah, it involved understanding the eigenvalues of this, the Hessian of the solution of the PDE. So it was quite a bit of work there. Yeah, and with that, I want to finish, not to take too much of your time, just telling you the name of the papers I have been discussing today. Thank you for your attention.
Thank you. Thank you for the talk. So if you have questions, this is the moment. And I think we can unmute people who have questions directly. If your questions have not been answered, I can unmute you, I believe, or Moss can help me. Any more questions? But I have a question which is about, I mean, this, right? The fact that the two values are not equal. You say that specific entropy is equal to this infimum, which looks like some sort of convex duality or something. If you have homogeneous diffusion somehow, right? With smooth sigma. And then you said that at the end, if sigma depends in time for the case, for example, of this Aldous Martingale, it doesn't work. I mean, is there, I mean, I have the impression there is a lack of convexity somewhere if you make it sigma time dependent. Is this the conjecture? Is there a way of seeing that? I don't know.
Yeah, so, okay, for this equality result, yeah, I would expect that, I think much more essential, for instance, is to be bounded away from zero than time independence. So I would assume that you can have time independence in a okay way with suitable assumptions and still get the positive result as long as you're bounded away from zero, for instance. I think, but that is still not sort of.
I mean, your sigma, right? It is sigma of mt divided by 1 minus square root of 1 minus t, right? So this thing is still moving until the
that would be, of course, beyond this. No, I meant, like, for instance, it's sigma is Lipschitz in time and in space. I would hope that if you are in the setting of Ito theory for SDEs, that you can have a positive result. But yeah, I'm not completely sure about being away from zero. Maybe it helps, I think, but there are examples. For instance, if M is geometric nonlinear motion, then the formula still works. So here you put its volatility and it works. So maybe the better conjecture would be sigma can even be, go to zero, but not too badly, something like this. So the weakest, so how far you can push this, I'm not sure. I think some level of time dependence, yes, but getting rid of being bounded away from zero, maybe.
Okay. Okay. Thank you very much. I don't have any more questions, and you are right. Making interview in the increments doesn't work at all. I did the computation, and you are it is the same value. It is the same value. So if there's no more questions, well, thank you for this great talk. We will have another talk in 1 month. It's scheduled and it's on the webpage. I think we have 2 junior speakers in about a month. Thank you very much for joining us. Thank you to Julio for this great talk, and see you next time.